Hi students, this is going to be another one of those review videos for those of you who need to have a little bit of review. In this video I'm going to be talking about two different concepts. Hypothetically, before this you should know like where different chemicals are going to be, or chemicals, ions, what can go through a membrane and where they're going to be more plentiful. This is going to be talking about two of the things that are going to play off of that, specifically different types of transport and then neurons and resting membrane potential establishment. Um, because I'm in my basement, that means that I'm going to be awkwardly off camera for a good chunk of it. So if you see a disembodied voice and a hand, that's why. Remember that we have a variety of different types of things that are going to be set up for the plasma membrane. And that within this whole entire setup of the plasma membrane, we're actually going to be looking at this portion of the board. So I'm actually going to zoom in on that now. Okay, so this is about as zoomed in as I can actually get with the limited technology that I have. And if you actually saw the technology that I had, then you'd understand that really all it is a webcam sitting on top of a stool on top of a bunch of boxes. And it's about, I don't know, a foot away or a foot and a half away from my whiteboard. So this is about as good as I can do, given what I have. One way or the other, this is going to be representative of some sort of cell. Obviously, we have the inside of the cell. We have some sort of extracellular surface here and an intracellular in here, an additional extracellular on this side. So imagine that this might be, lumen of the intestine and blood, or inside of the kidney and outside of the kidney, blood, something along those lines. We also have a variety of different types of ions that are going to be colored in different colors. And a couple of other different types of things. So first off, as we talked about before, we can have things that can just go from the outside to the inside through simple diffusion. If you want to go through that, you can go through that in the other video. In a variety, so that would be something like this. So that would be the equivalent of something like oxygen that can just go straight through, or lipid-based small hormones. If it's too big, it's not going to fit. We can also have facilitated diffusion. So these would both be passive transport. So it's going to go through following its electrochemical gradient. This one is a co-transporter. This is an anti-transporter, or an antiporter. But the co-transporter, there's going to be the black one that is going to be using secondary active transport, because in order to set up this whole thing, to set up the gradient of the green to go in, we have this type of pump that is going on. We have some sort of primary active transport. So this is primary active transport that is going to move this out. So the movement of this black in, so for example glucose, would be dependent on the movement of this green out. So that could be, say, sodium. And then we'd have sodium being pushed out through this pump. So imagine that it could be a sodium-potassium pump or something else. We can also have antiporters. Antiporters are going to be slightly different. If we're trying to push something out of the cell by using sodium to move it in. So for every sodium that goes in, something has to go out, but this would also still be an example of a passive or secondary active transport. And then we can have this glucose be moved to the other side of the cell. So when we're talking about something that is going to be active transport is going to be directly using ATP. Passive transport is going to be using just electrochemical gradients. And secondary active transport is going to be using movement or ATP that is supplied by something else. So the electrochemical gradient set up by an active transport that is moving something that isn't just the active transport thing. So not just the sodium. We also have drawn up here a G protein coupled receptor, or a GPCR. So G-coupled protein receptors often do a couple different things. So that there's going to be something that will bind to that receptor. The receptor will then have different subunits that are going to dissociate. So generally we have an alpha subunit, a beta subunit, and a gamma subunit. And the alpha tends to go and do one thing, the beta gamma tends to do something else as a couple. Oftentimes what that alpha subunit can do is it will open up a channel. So I'm going to just erase this whole entire mess, and we can talk about it in a slightly different type of way. Imagine that we have a situation like this. We have calcium channels, and then we have tethering proteins. That we know that when calcium hits a tethering protein, then that calcium is going to cause it to contract and release the goodness, whatever is inside of this vesicle, out of the cell. So when calcium goes to this, then that will happen. Okay. Our GPCR, the alpha subunit, can do a couple different types of things. One of them is release calcium stores from inside of sarcoplasmic reticulum, or the endoplasmic reticulum. It doesn't really matter, but generally within calcium vesicles. So the alpha subunit can do that. Another is that it can go and associate with some sort of other channel to keep that channel open. Generally, this would be involving some sort of cyclic GMP or cyclic AMP to keep that channel open. So that is what the alpha unit or the beta gamma units can actually do. Generally, it's not the GPCR itself that's doing something. It's having these two subunits, the alpha and beta, dissociate to go and do something. Release calcium stores or open up a cyclic GMP or cyclic AMP channel. The other type of receptor that we can have is a ligand-gated receptor, and that essentially just means that something is going to bind to it and it's going to open, and then something will go through. So for example, if we're talking about the nicotinic acetylcholine receptor, that is a good example. For G protein coupled receptors, the muscarinic acetylcholine receptor is a very good example of that. There's also a variety of different other types of receptors that we can talk about.